Topic 2 is visualizing numbers. We use what's called a number line to visualize the set of integers. So a number line only has one arrow on it to indicate which way the numbers are growing. You don't put an arrow over here. That is incorrect. Only on one side. And generally, you try to put 0 in the middle. But sometimes, if you're only dealing with like big numbers, and it's okay to, or very, very small numbers, or very, very negative numbers, it's okay to not have a 0. That's fine. But typically, you try to put 0 in the middle. So here's a positive integers. They are to the right of 0. And negative integers are to the left of 0. So this gives us a visual tool of the natural numbers. Now, here's the thing. There's only 9 numbers right there, right? But between here and here, there are infinitely many numbers, because numbers fill up the space between 1 and 2. Infinitely many numbers do. You could count forever and not finish them all. And what numbers are they? They are, first of all, the rational numbers. And guess what the symbol for rational number is? It is R. Very good. Oh, you're so smart. Gold star. Where's it? Okay. Rational numbers are ratios of 2 integers. And these are what we discussed in the last topic. Fractions. 1/2. 1/2 goes right between 0 and 1. 3/4. 3/4 goes about 3/4. Well, it is 3/4 of the way between 0 and 1. Okay? So rational numbers are written A divided by B, where A and B are integers. See how neat that's written like that? Okay. Alright. And then you could formally put this in set notation. Uh-oh, there's one exception though. I forgot about. B can't be 0. Why not? You can't divide by 0. You can't divide by 0. A could be 0. B cannot be 0. Okay. Facts about these rational numbers are the same as the facts about fractions. The top number, A, is called the numerator. And the bottom number, B, is called the denominator. And a fun fact, division is now included. Division is closed on the rational numbers. Provided you do not divide by 0. Divide, D-I-V-I-D-E, by 0. Okay. So division is closed on the rational numbers provided that you do not divide by 0. Okay. Now, there's a formal way to graph these, and I'm going to get another piece of paper out here, because there's a fun fact about rational numbers. Oh, let me write it first. I know you're dying to know. Rational numbers can be converted to a decimal Rational numbers can be converted to a decimal by division. Okay, so you divide the denominator into the numerator. The decimal form either terminates, which means it stops, or infinitely repeats the same set of numbers, group of numbers. We'll just call it group. Okay. All right, so let's look at some examples. We should know 1/2. What's half a dollar? 50 cents. Where does 50 come from? Okay, it comes from this. 2 goes into 1.0. All right, so let's divide. 2 does not go into 1. When we divide decimals, the decimal sign goes straight up. And 2 goes into 10 5 times. And 5 times 2 is 10. The decimal terminates. So 1/2 is 0.5. You can put a 0 at the end there. It actually infinitely repeats zeros, but we normally don't put that. We call it terminates. So 1/2 is 0.5. Now I used to call this, when I used to teach this, how to keep an idiot busy. How to keep an idiot busy. 1/3. Let's look at 1/3. Okay, so again, the decimal goes straight up. 3 goes into 10 times. 3 goes into 10 3 times. And 3 times 3 is 9. And you subtract, and you get 1, and you bring down a 0. Look, you get 10 again. 3 goes into 10 3 times. 3 times 3 is 10. Oh, 9. You subtract, you get 10 again. 3 goes into 10 3 times. You see the little... You see, you could just go on forever. Okay. Most times, we do not go on forever. That would be pointless. But what we do is we find the portion of the numbers that repeat, in this case 3, and we put a bar over the top, and the bar is called a repetend. This means that 0.3 repeats forever and ever and ever and ever and ever and ever and ever, never stops. Okay, never stops. So now if we look at the number line, you may not know where 1/2 and 1/3 are exactly. We're just going to put 0 and 1 on here because these are both between 0 and 1. But we can see that 1/3 is 0.3 bar, so it's going to be before. I'll say this is, we could go into tenths here maybe. Right there is 1/3, and then halfway between is 1/2, or 0.5 would be next. So we can use this number form to graph the fraction on the line if we don't know exactly how the fraction looks like in relation to its position in between two integers. Okay? Got it? Alright, so let's do an example here. 9/4. Okay. Express 9/4 as a decimal. Okay, so again we take 4. The denominator goes into the numerator. But in this case, this is what kind of fraction? So we know that this is going to be bigger than 1. And it is, because 2 goes into 9 twice. And 2 times 4 is 8. And we subtract. And there's the decimal. And now 4 goes into 10. How many times does 4 go into 10? Twice. And 2 times 4 is 8. And then we get a 2 and we bring down a 0. And then 4 goes into 20 5 times. So that's 2.25. And it terminates. 4 times 5 is 20. And we get 0. So that terminates 2.25. Or, if you remember that we did that 4 times 4 goes into 9 twice, remainder 1, right? Or you could say 2 1/4 in fraction form, right? How would you say that? 2 1/4, right? How much money is that? 2 1/4. Pretty neat, huh? 2 1/4. 2 1/4. Okay, good. You can't always check it like that, but if the denominator is 4, you can. Okay, what about, let's do one with 7 in it. 6/7. Okay, this one's a little trickier. Okay, so the denominator goes into the numerator. And I'm going to put a couple zeros out here because I know I'm going to need them. Okay, 7 doesn't go into 6, but 7 goes into 60 how many times? 8 times. And 8 times 7 is 56. And we subtract. We get 4, bring down a 0. 7 goes into 40 5 times, and 5 times 7 is 35. 40 minus 35 is 5, bring down a 0. 7 goes into 57 times. 7 times 7 is 49. 50 minus 49 is 1. And then we have another now. Bring down another one, because we haven't repeated yet, right? Okay, so 7 goes into 10 once. 1 times 7 is 7, and we get 30 left. And 7 goes into 30 how many times? 4 times, and 4 times 7 is 28. Now we have 20. 7 goes into 20 twice. There's 14, and look, back to 6. So if you're back to exactly what you start with, unless this is 2 digits, then you'd have to go to 60, but we're not going to do any of that hard. So now we can say that 6/7 is equal to 0.857142, all with a bar over the top. Okay? All right. So those are part of the numbers that are between these two. Right? We got the rational numbers. Now, I said that rational numbers either terminate or repeat a decimal. So you have to assume that there's the opposite of that. Neither terminate. So in other words, they never stop and never repeat. And those numbers are called, and they do exist, irrational numbers. Irrational numbers. I need it. Pi is an irrational number. But we're going to use a different example first. Okay. And most of this is an approximation. Because whenever you write an irrational number, it has to be an approximation, because irrational numbers never stop and they never repeat. So in decimal form, they have to be an approximation. But if you're comparing it with a rational number to see where it goes on the number line, you just use as many digits as you need to see which side of it goes on, the left or the right. Okay, so here's our example. I don't think we'll need any more though. Yeah. Okay. Square root of 3 is an irrational number. And I'm going to show you kind of why. Okay, rational numbers can also be put as a quotient of two integers, right? Rational numbers, they're a ratio of two integers. Irrational numbers cannot be expressed as two numbers divided by each other. Two integers divided by each other. Another opposite. So square root of 3 cannot be represented by two numbers divided by each other. Can't happen. Okay, so let's get back into this and talk about square root of 3. Okay, so we'll start with a good approximation, 1.7. Okay. So you could say the square root of 3 is approximately 1.7. So if we square 1.7, what should we get? 3. Right? The square root of 3 is this, so to go back to 3, you square this to get that. Okay, so let's square this. 7, I want to do the math kind of quick here, so. Alright, so this is 289. So we're kind of off, right? Nowhere close. We should be getting, the more digits I put out there, the closer and closer we should get to 3. Alright, so the next. No, because 1.5 times 1.5 is 2.25. Because 15 squared is 225. Square root of 3 is 1.73. Let's see if that gets us closer. So we'll do 1.73 times 1.73. And I'll use my super math skills here to get this done, maybe, if I have them. See if they come along. I need to put 2 zeros there. Alright, so we got 9, 2, 5, that's 9, 9, 2. Alright, now we're a lot closer to 3, huh? Yeah. So this is a better approximation of square root of 3. Let's put one more digit out there. And you'll see my super multiplication skills here. You're multiplying this out by hand as I write this, right? I knew it. Four, 2, 9, 1. Oh, now we'll run out of room. Should move that over a little bit more. 1, 7, 3, 2. Okay, so 4 and zeros is 4, 6 and 6 is 12, 10 and 8 is 18, carry a 1, that's 4, 5, 9, and 9 and 8 is 17, carry a 1, even closer. No, we're not. That's closer than that. Okay, I think the instructor did a bad job of multiplying. I think that's what happened. I think that's what happened. Let's see. 2 times 2 is 4. 2 times 3 is 6. That's 14. Carry 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 7 is 21. 3 times 1 is 5. There shouldn't have been a 1 there. Oh, I carried a 1 there. Okay. 2 zeros. That's 14. 7 times 3 is 21 with the 1 carried. That's 21. So that's 22, right? And then 7 times 7 is 49. 49 and 2 is 51. And this should be 1, 2. Okay, that looks better. Okay. All right, let's add this up now. Let's see, 4 and 0, 0 is 4. 6 and 6 is 12. Carry a 1, that's 18. Carry a 1, that's 5, 9. 5 and 3 and 1 more is 9. 2 and 7 is 9. There. Better. Yay! It might not be completely close, but it's closer to 3. Okay, so you get the point. As you put more digits out, and you could, I want you to square this on your own. And you should be pretty close to 3. In fact, if you put that in your calculator, it's probably going to say 3. But it's not 3. It's going to be 2.9999. The point is you'll never get 3. Ever. Ever. Because that's impossible. Okay? Ever get 3. Because this would be a rational number, and it's not. If you could get 3, this would be a rational number. Every time you get close, I mean, you're going to plug this into the calculator and say, it'll say 3, but it's rounding it up. Okay? That's why if you did this by hand, you wouldn't get 3. You'd get 2.99999999999, probably a whole bunch of 9s and then some, Okay, the other irrational numbers, as you said, are pi. And we never say pi is equal to. Pi is approximately 3.1415927. ... And another one is E. And E is huge. We're going to use a lot of E, especially in calculus. E is very popular in calculus. E is 2.71828. 2846 ... E is pretty much what you use, just like pi. Yeah, that's another topic. That's a lesson amongst itself. Okay. Yeah, that's for another day. Okay, but E is used a lot in finance. A lot. And that's where it's going to first be introduced, is in financial problems with compound interest, which is probably not in this course. It's probably in the next course, or maybe even the next course. I don't know. Okay, so now that is how we split up the different types of numbers.